So far, this whole taking the area between two curves thing doesn't seem too difficult. There's one thing we can do to you to kind of kick it up a notch, and that is, what if the two curves switch places? What if for one section, say, one curve is the upper function, but then for a different section of the region, a different curve is? Well, at that point, you have to remember the area between the curves is always best written as the absolute value. So if you had to take the absolute value of f of x minus g of x, for example, dx, then what you have to do is break it into multiple integrals. Now what that means, let me just kind of give you a little arrow here. What that means is you'd have to find a value c, so that for one region, say you're doing f of x minus g of x, but for the next region, you're doing g of x minus f of x. You reverse the order. That's why I don't really like using the minus version of breaking it up when we do distance and displacement, because we actually use positive here as well. One of the many reasons I don't like it. Okay, so let's do an example here. We have a region that's enclosed by two curves. We have j of x, which is equal to the cosine of x, which is rather obviously this pink curve right here. So that's j of x. And then we have L of x, which is the sine of 2x, which is this one right here, like that. Now, we want to find the region between those curves between pi over 2 and 3 pi over 2. All right, so pi over 2 is right here. 3 pi over 2 is right here. But here's the trouble. For this zone, the pink one is the one that's on top, the upper function. But for this zone, L of x is the one that's on top. So we're obviously integrating with respect to x. I mean, that's not even up for debate here because everything's in functions of x. So we're integrating with respect to x. So that means that our width will be dx, which means we'll be making vertical boxes. So if I think of a vertical box over here, it has width dx, right? And it has length that is upper minus lower. So it's L of x, the blue one, minus j of x, the pink one. Okay. Now over here on this zone, if I made a box over here, that has a width of dx as well, but its length, the pink curve, is on top. So it's j of x, which is cosine of x, minus L of x, the blue one, which is sine of 2x. So we can tell that over here we have this as our integrand on the left side. Over on the right side, we have its opposite as our integrand. What we need is the value of c in the middle. We need to know where this intersection right here happens. Okay, so we need to find that value because we're not going to be able to find the integral until we can find the value at the point of intersection, the x value at the point of intersection. And I need the x value because, of course, I'm integrating with respect to x. If it was respect to y, then I would want the y value of the point of intersection. So I want x equals c. Okay, well, point of intersection will happen when the two functions are equal to each other, when j of x is equal to L of x. So that means that the sine of 2x is equal to the cosine of x. Now, for me, as a math instructor, little alarm bells are going off in my head because I know that the sine of 2x is 2 times the sine of x times the cosine of x. That's one of the double angle identities that we learn in pre-calc. You don't have to memorize it. You just have to be able to go look it up on a sheet, right? But we do have double angle identities. All right, so now you might be tempted to divide by cosine, but that would be an unwise move. You don't want to lose your cosine values or what solutions you get from that. What you want to do is actually subtract cosine of x from both sides. I know what I'm doing, trust me. So this would be 0 equals 2 sine of x cosine of x minus the cosine of x. Now there's two terms there, and they both have a cosine in them. So I could factor out a cosine of x. That leaves me 2 sine of x minus 1. Now, if two things are multiplied and make 1, we know from the multiplication property of 0 that one of them is 0. We learned that in algebra class. Well, the cosine of x is 0. Let's think about where that happens. Let's think about a unit circle. The cosine of x is equal to 0 up at the top and the bottom of the curve. So this would get us x is equal to pi over 2 and 3 pi over 2. Technically more. I mean, there's 5 pi over 2. It just keeps going and going and going. But obviously these two are the ones that we want, because they gave them to us in the problem. They said they want us to go from pi over 2, here's pi over 2, to 3 pi over 2. No problems. Okay, so I got those two. Great. That's not C, right? C is between the two of them. So I need the value for C. Okay, well, let's think about this. If I look at this, this would mean if I add 1 and divide by 2, it would mean that sine of x is equal to a half. Now, where does that happen? Sine is the y value on the unit circle, so the sine of x is equal to a half in two positions. It's over here. Let's see if you remember. There's an angle that has the square root of 3 over 2 and a half. And then it's over here at negative square root of 3 over 2 and a half. Do you remember? Because this is pi over 6, and this is 5 pi over 6. And then technically it's 13 pi over 6, and so on, 17 pi over 6, etc. So this would mean that x is pi over 6, 5 pi over 6. Technically, if you keep going around, it's 13 pi over 6, 17 pi over 6, and it just keeps going and going and going. Now, which one's the one we want? Well, pi over 6 is right here. That's that intersection. So pi over 6, good. Pi over 2, right? So the blue one's on top, pink one's on top, in pi over 6, then the blue one's on top. Pi over 2, now the pink one's on top. And this is 5 pi over 6. It's got to be the one that we're looking for. So it's got to be this one. This one because it's between pi over 2 and 3 pi over 2. All the rest of these are past where our graph shows. They would hit up again later, but we don't need to see those. So that means that C is 5 pi over 6, and that's what we'll use in order to break our integrals up. But we'll do that on the next page because we don't have any space left on this page. That's why I gave us 2 pages for this problem. Okay, so I want to break up my integrals into, I have one that goes from pi over 2 to 5 pi over 6. There's my C value. And it's going to have, now let's see, for this first zone, it has j of x minus L of x. Oh, I'm sorry, I did that first zone in purple, so I'm just going to keep my colors consistent here. So it was from pi over 2, and then it was j of x minus L of x dx, because that was the width. Then I'm going to add to that the other integral. Well, the other integral goes from 5 pi over 6, that C value that we found, to 3 pi over 2, but it reverses the order. So it's going to go L of x minus j of x. dx. All right, lovely. This shouldn't be too bad. Okay, so we are going to kind of, you'll see, we're going to kind of flub our way out of something here. But let me write this first. So this is pi over 2 and then 5 pi over 6. J of x was equal to the cosine of x minus the sine of 2x dx. And then I'm going to add to that, I'm dropping a little bit of my color coding. It was getting a little crazy there. 5 pi over 6 to 3 pi over 2. And then it's going to be sine of 2x minus cosine of x. Now, we have just a little bit of a problem, and we're going to kind of flub our way out of this. And this is going to be very common with us, so pay close attention. You see in here how we have a sine of 2x? See that? Now, technically, both of those pieces of the integrands require u substitution. But I have no desire to break my integral up into 4 integrals. I mean, it's already bad enough with 2. So I'd have to do this integral from pi over 2 to 5 pi over 6. Then this integral with some kind of u sub. Then this integral with some kind of u sub. And then another integral from 5 pi over 6 to 3 pi over 2 of cosine. Blech. So we are going to wiggle our way out of u substitution right now. And this is going to happen to us a lot. So I'm going to star this. Wiggle out of basic, it's not really wiggling out of it. You're kind of showing, not showing all the work. You're skipping steps in very basic, i.e. u is linear u substitution. We will do this a lot because it's just not worth it. When u is something very simple like a line, matter of fact, this is what it used. So mx, right, 2x. When it's something very basic, we're going to skip the steps. All we're going to do is kind of show, look, u would have been 2x, right, for both of these. Well, then what's du? Du is 2dx. Oh, my stars, but I don't have a 2. So I'll just say 1/2 du, right? And then we would have to go substitute them in and change the numbers and blah, 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 blah. So what we're going to do is kind of skip it. So watch. Pi over 2. Oh, sorry. We're going to actually take the integral. So the integral of cosine is sine, right? So that integral right there becomes the sine of x. Okay. What's the integral of negative sine? So it's cosine, right? So it's cosine of 2x. And it's positive, right? Because it's negative, right? So this negative sign, so the integral of negative sine is positive cosine. But there was a 2 in there. If I took the derivative of this right now, I would not get that because the derivative would have a 2 because of chain rule. So what you do is you use this and you put a half there. Right? That's where you would get to if you did u substitution. You'd have a half times the integral. Now notice you can take the derivative of this. The derivative of cosine is negative sine. The 2 and the half would multiply and make 1, and you'd have a 2x still sitting in there. It would work with chain rule. Sneaky, huh? We're going to do this a lot because it is not worth it to us for very basic u sub to show all that garbage. And so we're going to go from pi over 2 to 5 pi over 6 on that one. And then we're going to add to it. And then we're going to do the same thing over here. So if you didn't get it the first time, let's see if you get it this time. The integral of sine is negative cosine. I'm leaving myself some space of 2x. But that's not going to work because the derivative of cosine of 2x is 2 sine of 2x. So I need that half. So I put the half right there. Right? So, oh, I forgot to put parentheses around all this. There we go. That one and then this one. So negative 1/2, right? We just use that piece. Plus, and then, well, it's actually going to be minus because the integral of cosine is sine. And since there was a minus in there anyway, that's going to be minus sine. Oop, minus sine. Sorry. And we're going to take that one from 5 pi over 6 to 3 pi over 2. Okay. Well, we're not in basic math class. Like, we don't have to sit here and like show all of our substitution. Let's get real here. This is what Desmos has been invented for. Oh, and here's the graph in case you're interested. So I actually took the integrands that I knew I needed, which is sine of x plus 1/2 of cosine of 2x. And I'm just going to find f of, what did I want? F of 5 pi over 6. There, it's 0.75. And then I want f of pi over 2. There we go. And then I want g, this is the integrand of the other one, so g of 3 pi over 2 and g of 5 pi over 6. There we have it. So I can use these values, right? So it's 0.75. This one is 0.75 minus a 0.5, right? Hello, Desmos. Plus, and then when I put these numbers in, I'll get 1.5 minus a negative 0.75, right? Because there was a minus already in there. And I will just say Desmos. So that way my instructor knows that I did this with computer. And then this number right here, well, I mean, I can just do all of this, but this is 0.25, that's 1.5, so that makes 1.75. 1.75 plus 0.75 makes 2.5. And then I think I gave it a unit. I think it was inches. It is. It's inches. So therefore, this is 2.5 inches squared.